Please like and subscribe to this channel and press the bell icon to get new video updates.
Okay, so today we're going to have a little discussion about NASA wideband space communication. And the reason we're doing this is we're really right in the process of transitioning from radio, what we've been using for the last 60 years of radio communication, to optical and laser communication in space. So this is actually something very new, and we've only been investigating this and testing it for about the last dozen years or so. So there's a lot of, as I explained before, there was a lot of reasons for that, but we'll get into those. So on the next slide, that's an introductory slide about me. I don't know if you can see that slide. Can everybody see that? And you'll notice that's a picture of the Earth. Everybody see the Earth there. And of course, that's a image from a weather satellite that's being collected once every 30 seconds. And you'll notice that there's a little black dot that goes over South America real quickly. That's a full solar eclipse. So that is a solar eclipse as seen from space. So it was last year in 2020, and I like to show that to the people when I'm doing my solar eclipse seminar, so that they can get a chance to see what a solar eclipse looks like on the Earth, but looking at it from space. Now, the other reason I show this is I led the team that built this telescope and this for this satellite, so it's part of my in my bailiwick, if you will. I built that for Goddard Space Flight Center in 2008 through 2010. So that's kind of an introduction to who I am. I'm also obviously an astronomer and a ham. K2NAX is my call sign. I know quite a few of the members of AWA, even though I've been delinquent into going down and visiting. I know I should do that. Anyway, gosh, last year at NASA, we had an unbelievable year. I'm not sure how we'll ever equal it in the next few years to come, but with James Webb Space Telescope up there, downloading these amazing images on an almost daily basis, we're getting just amazing imagery from it. It's been just spectacular. Almost every day you wake up and they've got some new discovery. They also did a mission called DART. I don't know if you've heard about DART, but it was the very first planetary defense mission where we actually impacted an asteroid and moved it in its orbit. So it was quite an event last year. Of course, Perseverance and Integrity, that's the helicopter drone that we have on Mars, is doing amazing science. And I don't know if you're caught up, but last week they found organic chemistry on Mars again. And again, you know, we're able to establish that, yes, life could be possible there in those locations. So good news there. And of course, we are going back to the moon. And so we made another moon shot last year on November 18th. We all stayed up at 1:40 in the evening to watch it. And that was an amazing event. We were cheering it on because we had some of our doubts whether Artemis would ever get off the ground. But, you know, fortunately, with all the hard work down there, they got it off the ground.
Since 1958, NASA has relied on radio wave technology to talk with missions in space. Today, we're developing a better way to get spacecraft data back to Earth. That's where the Laser Communications Relay Demonstration, or LCRD, comes in. Built and managed by NASA's Goddard Space Flight Center, LCRD will send and receive near-infrared laser beams to and from Earth. As NASA's first long-duration test of optical communications technology, the mission aims to perfect space and ground-based technologies. So why lasers? Laser communications can transmit up to 100 times more data per second than previous systems by using a shorter wavelength of energy. With this increased bandwidth, missions can send larger files and even live high-definition video from space. Laser communication systems are smaller and more efficient than radio wave technology. They leave more room for science instruments, are cheaper to launch, and require less energy on board the spacecraft. These benefits extend to receivers on the ground. Earth-based laser communication receivers can be up to 44 times smaller than the current radio antennas. LCRD is the next step in making these technologies a reality, helping NASA to push the boundaries of scientific discovery and exploration. Eventually, NASA will integrate this technology into future missions, as well as share it with commercial companies.
So our next step in communication will be lasers. Finally. We're going to go over NASA's use of radio communication, because that's kind of a fascinating story. But for a learning objective, we'll talk a little bit about the transition to optical. And there's also some international efforts that are going on in Japan and Europe for laser comm. And then what are some of the future missions that we're going to use laser communication on and try to get that HD video back from these satellites in real time. So that'll be interesting when we get to that point in our development for laser comm. So space communication down through the years has been, a radio-based technology. So when we talk radio, we're going to talk narrowband and wideband. And so I wanted to set a couple definitions. Narrowband with an uplink and downlink in RF would be basically VHF through C-band. So in the kind of ranges that we're more familiar with, C-band being 5 gig, so VHF through around 5 to 8 gig. And the classic definition of narrowband is any telemetry or any data communication under the coherence limit of the frequency, i.e. no multipath interference. That really doesn't apply to space. So in space, we don't kind of use that definition. We just sort of cut it off at C-band, S-band and C-band. Those are our, and we'll get into definitions of those in later. But we then talk about wideband being, that would be over the coherence limit of a terrestrial communication. But again, in space, it doesn't really have the same meaning because it's not bouncing off things in space. So we don't have that issue with multipath. So we really kind of define wideband as X through KA and up to V and W, the very higher frequency. And although we stop that dish on the right there, that's a KA band 32 megahertz dish that's in Goldstone, California. So we tend to stop in space communication at KA band. So that's the definition of wideband. Narrowband, what we're obviously transmitting is telemetry and command data. That's right. Basically, these definitions are right off the extra class test, telemetry and command. So you'd probably be familiar with that. And so we're going to go through a little bit of the background of this in NASA space communication from the early days when we were talking to satellites in the VHF, UHF, and lower frequencies with smaller antennas that it was basically, we consider it near Earth. Back when NASA was first founded in 1958, it became immediately evident that those wavelengths were never going to transmit the volumes of data that we needed to transmit to get imagery and data sets back from instruments. And so when it came time to go to the moon, MIT and JPL got together and they developed a 4-band, we call unified S-band, where we're using 4 sidebands of the S-band signal all at the same time to transmit the Apollo moon mission data sets. And so they had improved the technology of the lower bands quite a bit by the Apollo years, and far surpassing the existing radios for Mercury and and Gemini. But when we got to 77, we had an ambitious program where we wanted to go to Mars and to the rest of the planets. And so we had to develop much, much larger antennas that could receive signals from billions of miles away instead of just, a few hundred miles away, or maybe the moon a few 100,000 miles away. They wanted to receive signals, low wattage signals in the range of 5 to 10 watts from 1 billion to 4 billion miles away for these satellites that are going farther and farther out in the solar system. So we developed a 70-meter antenna system, which was installed in 3 locations in the Deep Space Network. And we developed a cryogenic Ki band amplifier to go with it, which we'll talk about later in 77. And that was what we used. That's what NASA used for 35 years. So that was current technology. Now, toward the end of that, we did develop SDRs, software-defined radios, because we were able to make them much, much smaller and lighter. And so we'll cover that later. But LaserCom doesn't come on the scene until 2013, when they launched the first laser communication satellite, and they put it in lunar orbit so that they could really ring it out from a long ways away. Wanted to get it a couple 100,000 miles out there and really ring it out. So LLCD went out there in 2013 and had very successful tests. I'll show a video on that later. And it leads us to the present day, LCRD, which is the current demo up there right now. And they are currently ringing that system out. And hopefully we will get to the point where we can put it up operationally on one of our deep space probes. And we currently have one that's being prepared to have LaserCom. It's called the Psyche mission. We'll talk about that later. Of course, the problem with RF communication is you've got this R squared term in the denominator affecting your transmitted power. And so its propagation loss is going down by the distance squared. So you have to build a very, very large antenna. The receive antenna has to have a lot of gain to offset that. And so because of that awful distance that we're talking about in the billions of miles, right now we have a satellite that we still can talk to, and it's 14 billion miles away. So believe it or not, we've been able to overcome that propagation loss of that, R squared term of 14 billion miles. I don't know how they're doing it, but we'll take a look at what they'll tell us about it. But they use, of course, a very, very, very large antenna to do that. So if we were to sort of take an approximate, something that we would have a feel for, if you were to consider that your smartphone talking to your smartphone tower has a relative difficulty of 1, and so that smartphone is about a half a watt in that range. I think it's around 0.6 watts, and it's talking a kilometer or 2. If that's a relative difficulty of 1, your television station 10 kilometers away has a relative difficulty of 2 orders of magnitude above that. The International Space Station has a relative difficulty of over 5 orders of magnitude because it's 400 kilometers away. If you were to communicate to a satellite in GEO, which you do all the time over your telephone for long distance service, that's about 1 million times more difficult. And if you want to talk to Mars, that's 10 to the 16th times more difficult, because that's just how your propagation is falling off to get that distance of 300,000 kilometers. Now, if you need to go outside the solar system, you're talking 10 to the 18 and 10 to the 19 times more difficult to talk over a half a watt transmitter, which is about what we're talking about on these transmitters, in that range, a half a watt to 5 watts. So it is, again, this gives you the perspective of how difficult it is for RF to achieve these these communications. But the technologies that have been developed, amazingly, have really done the job. Now, of course, when you get up in frequency, your beam becomes much, much more narrow. And that S-band beam right there has a very broad beam, and it's easy to set your antenna. But when you get down to Ka band, 26 to 30 gigahertz, it's a very narrow beam that you're utilizing. And so the beam width, of course, decreases. And then if you're going to go up into the optical bandwidth, the beam width gets very, very tiny in terms of antenna pointing. And so that becomes really the second big problem. Number one is generating the laser in the first place. The second big problem is pointing the antenna. So laser pointing, you can see here the divergence of a radio beam from the moon. This is just from the moon here in this picture on the left. And you can see the footprint of a radio beam versus the footprint of a laser, which is 10,000 times smaller than the radio footprint. So because the wavelength is 10,000 times shorter, the beam is much, much more difficult to point carefully. So that becomes one of the very, very big problems in this with trying to upgrade from radio to laser. Now, back in '58, the Mercury capsule actually had an antenna in the front end. I'd forgotten about this, but that little red stick on the front of the Mercury capsule, that was a UHF VHF dual band antenna, believe it or not. And all voice communication was UHF VHF to the Mercury astronauts, believe it or not. And they used command and telemetry with C-band, which was 4 gigahertz. And so, believe it or not, that's where we started in the heritage. I did put that table on the left, on the right there, in case anyone needed it for reference. That it gives you the band passes for those bands I just referred to, from VHF up to S-band, which is S-band is the most common telemetry band that we use, command and telemetry. X through Ka, those are the common data, or what we would call wideband. And Ka is the most common right now. We run that at 32 gigahertz. So all the really large antennas for deep space are operated at 32 gigahertz. That's really the only way we're going to get data sets out of an instrument like James Webb, where we can generate far, far more data than we could possibly cram through the communication section of a satellite. That's what's driving, of course, the need for a laser. Now here we have, basically we started out with what we call a near-Earth space network. So we had a spread of dishes all throughout the world to communicate with these orbiting satellites that we were using, at the time, S-band communication. Even with Apollo, it was that unified S-band protocol. So you could see we had to spread these antennas all over, including Antarctica. And we had one in Norway, way up near the North Pole, for orbits that went way up that way. And there's Australia mixed in there to cover the Pacific, and Hawaii, of course. So we had the near-Earth space network set up, but it soon became extremely obsolete because it just didn't give us the coverage we needed. It could not cover the whole globe. You can see there's gaps in the mid-Atlantic region, in Africa, there's gaps. Obviously, in Russia, there's major gaps. So this network was completely inadequate for the future of NASA space exploration, but it's what we started with. I did mention unified S-band. It was invented in '64, and it was invented to get the video data back from Apollo 11. Now, they tested it on Apollo 8. And so you can see in that amplitude graph on the right, you can actually see the data as it's coming through on the transponder. They developed it at Lincoln Labs at MIT, and it was a major breakthrough where they used the sidebands of an S-band frequency to get the data back, the video data back from Apollo 11. So it was a major breakthrough. We didn't have the ability to go higher band pass at that time. So that is how we did it back in the day. We did use, in the 60s, we did use S-band. So 2 gigahertz, believe it or not. Anyway, again, by the time we started going to deep space, we really ran out of room on S-band, and we needed to be able to take pictures, like even that little black and white picture on the left there, from deep space cameras and get them back through the Deep Space Network. Now, they actually invented digital photography for this satellite right here. That's Mariner 4. And they did a flyby of Mars, and that's a picture of Mars. And of course, that picture was extremely disappointing because they didn't find the aliens they were looking for. You know, they didn't find the canals, and they didn't find the seas or anything like that. They looked at that picture, and of course, it looks just like the moon. So it was a little bit disturbing, but NASA did invent digital photography to go out there and do this. But they also had to invent the Deep Space Network to go do this. And for the first time, they started sending and receiving much higher frequency transmissions at a much longer or much shorter wavelength. So they put together 3 sites on what they call the Deep Space Network. And so there you can see the 70-meter antenna at Goldstone, California. That 70-meter antenna, 230 feet across, that weighs 3,000 tons, is sensitive to, and get this, it's sensitive to 10 to the minus 18 watts. And they call that an attowatt. Actually, that number should say 1 over 10 to the 18 watts. I guess that's basically what it says here. 10 to the minus 18. So imagine how we get a receiver to that level of sensitivity is quite the struggle. So that's the dish that they built for the Mars mission in the 60s, and we still use that today, believe it or not. That mission that we sent out to for Voyager, that we sent outside the solar system, that's still transmitting 14 billion miles away, is being received by this dish every day. So we have one of these in Australia, one in Spain, and one here in California to cover the entire sky, deep space. Here's a picture of the cryogenic receiver. It has a very, very low noise 32 gigahertz amplifier. It's a 2-stage vacuum cryo cooler that feeds us 12 centimeter feed horn. It operates at 12 Kelvin, so it operates extremely cold. It's being manufactured by CTI Cryogenics, and it only has a lifespan of about 2 years of continuous operation. So the amplifier has to be replaced every 2 years. So they build hundreds of these things. They're operating 3 of them on the big antennas all the time, 24 hours a day in 3 locations. And they have 6 more for each location on the smaller 32-meter antennas, or 34-meter antennas. So the 70 and the 34s all have this cryogenic amplifier. And this is what they're leveraging to get this signal gain of 10 to the 18th power on these low noise signals. So there's also, of course, a lot of digital signal manipulation going on, a lot of error correction going on to achieve this 10 to the minus 18 gain that they need. And that's all going on, of course, in the background in the computers once they digitize the analog signal. So this is the analog amplifier, and right behind this amplifier, as soon as it's coming out of the plug there on the left, it's being digitized. So that is what we used for Voyager, the 70-meter antenna. Started in the 70s, still using it today, and still hearing Voyager there on the right at 14 billion miles. So imagine what that R squared over 14 billion miles will do to a signal. So people ask me all the time, why can't we hear all the other civilizations that are out there, obviously, that are transmitting constantly, and why can't we hear them? Well, the reason is because we can barely hear this, and it's close by. It's 14 billion miles away. And look what kind of antenna it takes to hear this satellite. And so even a high power television station or a high power radio station, millions of light years away, we would never ever hear it. It's just the signal loss is just too severe. So that's kind of, at this point, the answer to the question, why haven't we heard anybody out there? Because, you guys are hams, you know the answer. It's very difficult to receive these signals with that kind of signal loss over those distances. Okay, so current RF technology is on the right there. Those are the current boards we're using, and those are all software-defined radios. So the next-gen satellites, such as the GPS satellite there above it, is using a software-defined radio. It's extremely lightweight. The amount of power it takes is extremely low. It's set up to transmit in all the bands from S to Ka. It's, of course, full duplex. And it runs S-band at a really fast clip, 300 kilobits per second. It's pretty fast. It can run X-band even higher in the megabits per second regime. And we can even push that even further if we apply a lot of forward error correction to the data set. So that's the kind of the current RF technology, which we would probably expect to have NASA to be on the cutting edge of SDR, which they are, and they developed it 20 years ago at NASA Marshall Space Flight Center in Alabama. So the SDR signal looks about like this. They have that antenna, of course, on the front of the spacecraft, and they do have a analog amplifier. So a low noise amplifier, just like the ground station would use, but immediately, of course, they're converting it to digital and then going through the SDR. So very, very similar to what you would see in a ham radio, a software-defined radio that we would buy from Yaesu or ICOM. Very similar, but you can see on the left, it's in a radiation-hardened structure, box, if you will, that's been through a thermal and vibe test so they can survive the rigors of outer space. They can be exposed to solar radiation and keep on transmitting. So that's the current technology that we use in the RF regime. So to augment this, we don't use any longer, of course, terrestrial receivers for near-Earth satellites. We did use that near-Earth network that's on the upper left-hand corner, which have ground stations. We still have some of those, but what we have today is the space network over on the right that's headlined by a satellite we call TDRS. So TDRS is what our satellites are talking to. So that is what we would call a relay satellite. So even though we're talking RF to our satellites that are close to the Earth, the RF is going to another satellite, TDRS, which is in orbit around the Earth. And then TDRS is phase locked to the ground station. And so we're in constant communication with our near-Earth satellites, like especially the International Space Station, where the astronauts could pick up the phone at any moment of the day, and be on their comm and talk to someone on the Earth any time of day. So we're relaying that through a satellite called TDRS, which is our space network, a fleet of SATs tracking satellites that provide constant mission availability. Well, that's what we call mission availability to all of the missions that are near to the Earth. So near would be anything between us and the moon. So that would include all of the low Earth orbit stuff, like Hubble is low Earth orbit, and the space station. It would include the satellites in what we call mid-Earth orbit, which would be the GEO satellites, and then the stationary satellites, geostationary satellites. They're at about 23,000 miles up, and the GPS satellites are only 14,000 miles up. So all of that is communicated through TDRS. You know, in any given day, there's about 180 active satellite missions communicating through TDRS. So that is a really, really busy system, believe it or not. So that gives you an idea of the concept. Now, if you were to look at the Earth from the North Pole, that R there, if that was the North Pole, you would see the view of the Earth from the the ground station at Goldstone. They have, you know, and of course, 60 degrees past that would be the Madrid view, and then another 60 would be the Australian view. So, you know, we basically have a view, 120, and we have a view all the way around the Earth. So, of course, there's TDRS going around the Earth, and that is how we maintain coverage through the three, in current technology, through the three space networks to talk to the amazing array of satellites that are out there. I did have a slide on how many satellites are out there at any given time, but it's just too complicated. It's too much to look at. It just gives you a little bit of an idea. You know, there's the space station down here. There's Hubble over here. There's TDRS over the Pacific, TDRS over the Indian Ocean, over the Atlantic Ocean. And at any time, we can talk to our ground station through the relay satellites, through our S-band, through Ka-band RF communication. So that gives you an idea of where we are currently in our satellite communication. And there's the layout of the TDRS over all the, and you can see how many we have. I think there's 10 of them up there at any given time. So this is what it would, the green circles are the, you know, that's the ground stations that TDRS is talking to. And the red track, that's the International Space Station track. So you can see where it would be out of communication a lot of the time if it wasn't for TDRS, the relay satellite, that we can pick up the phone and get the data to the relay satellite and then right down to the ground. So that gives you an idea of where we have come from. All of that is run by SCAN. SCAN is the NASA Space Communication and Navigation Program. It was established in 2006, and it kind of took over all of this. It administers all of this for NASA. And so we call that SCAN, S-C-A-N. Administers all the Earth station and the satellites and even the near-Earth network. But you guys came on to talk about LaserCom, so much for history. Let's talk about LaserCom. Now, we started LaserCom in 2013 with LLCD.
3, 2, 1, 0 ignition and liftoff of the Benatar 5 with LEM, pursuing a rift about moon dust and the lunar atmosphere.
I see something.
that's when engineering is more exciting, when you actually get a result from your mission. So LLCD went up on a rocket, a satellite that was investigating moon dust, and it utilized a 1.5 micron infrared laser. Now, the reason we did that is you could see here the electromagnetic spectrum, and the problem we have, which is the atmosphere of the Earth is opaque to many of these frequencies. And we do obviously have the window in the atmosphere for optical, the visible window right here. That's how we can see through the atmosphere. We do have some slots for infrared, not that many of them. And of course, we have the massive radio frequency slot in our atmosphere, but you get too high in radio frequency and the ionosphere then absorbs it. So that is, of course, by design from somebody, some creator that wanted to keep the Earth safe. And the atmosphere is opaque to all the bad stuff that's out there. But fortunately, there's a few slots that we can use. And one of them is this one slot for infrared laser at 1.5 microns, or, just above visible light, or just below visible light, excuse me. And of course, 10,000 times above radio frequencies. So from 1 meter all the way out to, of course, 1 millimeter, 1,000 times smaller. Okay, so that's a little bit about the atmosphere and the problem with laser. So on that spacecraft, they had a telescope. It was actuated. It had actuators, two-axis gimbal, so they could point the telescope. And they had a little half-watt laser beam on that mission, and they transmitted a signal back to the ground at White Sands, and they received the signal. So it was a very, very successful mission, and they did proof of concept on this on LLCD back in 2013. So really good results on this, as you saw in the video. The interesting thing, of course, about LaserCom is not really the ground segment. That's just a bunch of telescopes, about 16-inch telescopes. You can see those on the right there, that they receive the laser beam in those 16-inch telescopes with 4x redundancy. They would transmit the laser beam up to the satellite with a 6-inch telescope, so you can see those on the top there. And they were using a 40-watt chemical laser. Because we're on the ground, we could do that. And we would transmit the data using a 40-watt laser. The issue, the real Achilles heel for LaserCom is that space segment, what we call the space segment. Now, we've done the optics for years, for 40 years. We can make 4-inch lightweight telescopes, no problem. It's the laser that's the problem. So we have got, because we can't put a chemical laser up there, we could, but we'd run out of fuel in minutes, right? So the chemical laser is just not going to do the job. So we have to use a laser diode. So you're actually looking at the picture of the laser diodes over on the left, and it's generating a signal into this optical amplifier, a fiber optic amplifier that's doped with erbium, which is a technology that was developed again by MIT and JPL. And that amplifier is getting the signal up to about, it's taking a milliwatt signal and getting it up to about half a watt. So the laser module on the left, the amplifier is here on the right, and we're taking a tiny little laser diode, a whole series of them. I think there's 8 of them in this picture. And we're amplifying that signal using a fiber optic amplification system. And we're getting it to about a half a watt. So that is the limiting technology of the architecture. And it becomes kind of the real problem with LaserCom. And that's why it's taken so long to get there. Is we really haven't been able to get over this hurdle all these years. So this was a picture from 2013, We've actually, there's the architecture, the receiver at White Sands here on the left. The instrument that was orbiting the moon is on the right. And it did get the data back. And I think I have this is an actual screenshot of the test. And they got it up to 600 megabits per second on the wideband data stream. So that's a gain of about 100x. That's the gain of about it. We normally would operate a wideband link at about 7 megabits per second, and we're operating this at 600 megabits per second. So very good results for that first laser test. And that was very encouraging once they locked the signal and was able to get those two telescopes to point at each other. And again, that's the second problem is you've got to be able to lock the system and get its pointing accuracy to where you can see it. So that leads us to the next mission, which was LCRD, which they launched in 2021. So LCRD was the second attempt. It went up on a DoD satellite called STP-SAT-6, which is a technology demonstration satellite that the DoD put up, and NASA rode along on it and put this laser palette on there. And again, it was pretty much the same telescope technology, and they used the same laser.
On December 7th, 2021, NASA launched the Laser Communications Relay Demonstration Payload, or LCRD.
And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
LCRD is testing revolutionary laser communications technologies, which can offer science and exploration missions more data than ever before. Over the holidays, we asked for social media users and NASA missions to share their New Year's resolutions with us using the hashtag LCRDresolutions. Today, we are happy to announce that we've transmitted those resolutions to space over laser links through the LCRD mission. But how did we send your resolutions to space? What is LCRD?
LCRD is this part of the spacecraft. Right. It's about the size of a king-size bed. It has two optical modules. They're basically telescopes that look down to the Earth and look at our two ground stations in Hawaii and California. Okay. So this is 10 scale. But this is a full-scale optical module. This is the telescope that will do bidirectional communications. So the lasers come into this telescope and will be going to the Earth and coming back.
Now that we are on orbit and transmitting data through LCRD, we're sticking to our New Year's resolutions. We're using LCRD as a platform for optical communications experimentation and showcasing the benefits that laser communications' high data rates can offer science and exploration missions. We've also launched T-Bird, a small satellite demonstrating NASA's highest ever space data rates using laser links. Soon, we'll install a laser communications terminal on the International Space Station, empowering astronauts on the orbiting laboratory with new communications capabilities. We are also furnishing the Artemis II mission with a laser communications system so NASA can transmit high-definition video of the next generation of lunar explorers. To learn more about NASA laser communications technologies, visit nasa.gov/lasercoms.
Very good. So that was our friends at SCAN that developed that video for us. This is kind of a look inside the telescope, and you can see the laser fiber comes into the transmitter. It does have a CCD receiver. It's actually an LCD receiver. And it has a fine steering mirror where it can do some of that pointing to get the pointing accuracy that's required for this kind of communication, where you have such a very, very narrow bandwidth. You've got to get your pointing accuracy to a much higher degree than a regular radio transmitter. So that's what the LCRD block diagram. And oh, by the way we lock it on, we phase lock it to a star. We have another imager up here on the top. We call it a star tracker. And we lock that imager onto a single pixel of a star. and that freezes this mirror in place so we know exactly where it is at all times. And that way, if the spacecraft moves, which it does because it's in orbit, the star tracker will keep this pointed in the exact position it needs to point to talk to the Earth. Okay, so the key to moving past, into the future is to be able to talk to other satellites. So it's one thing to talk about, talking to the ground, which we've done. We would really like to talk to the International Space Station. So the next project that's going up at the end of this year, we call it Illuma-T, and it's going to be a receiver-transmitter pair that's on another gimbal that's on the outside of the International Space Station. So the algorithm will be much more complex, obviously, because you've got a space station that's moving at 7 kilometers per second, another satellite moving in a different direction at 7 kilometers per second. So it's going to be much bigger challenge to get the tight beam width to lock its face on that receiver. So that'll be interesting to see if we can get the algorithm to lock. Now, during that test, I didn't have a copy of the actual test data, but they did get 1.2 gig out of that, which is approaching, 500 times faster than S-band. So that is really significant. And we're looking forward to Illuma-T. We can skip this slide. That's a little more complex. To get to Artemis, though, we need this migration path, which goes through T-Bird. Now, the video did mention T-Bird, which is going up this year in 2023. And they have had success with T-Bird, which is another infrared laser, but a much more powerful one. And eventually we want to get to where we can put a T-Bird module on Orion and be able to communicate from the moon with wideband optical. So that'll be the migration path, and hopefully that will be ready by 2027 when we do the next moon landing, which would be Artemis 3. So that's the current timeline. There's kind of an idea of what the beam footprint looks like. If you're transmitting, and I think this is actually from Mars. Yeah. So here's an idea. If we had a satellite around Mars, we could actually record the entire surface of Mars with our Mars Reconnaissance Orbiter. But it would take us about 2 years to download all of that data. So we just cannot do it in a timely fashion. However, with LaserCom, we could do that same download in about 9 weeks. So that's the pressing need to get this data chain up and running from a place like Mars or any of our deep space missions, starting with the moon, of course. There's T-Bird. T-Bird is a very small little 6U. We call it a 6U CubeSat. That's a very small CubeSat. 3U is a 3-inch by 3-inch cube, 3 by 3 by 3. So you've got 3 by 3 by 6 to define T-Bird, and then you've got 6 of them to make up the whole satellite. That's small sat lingo, CubeSat lingo. So we call that a 6U demonstrator. So it's a little tiny thing, but believe it or not, we have the electronics crammed in there to be able to do LaserCom. And the way we point this is we actually point the whole satellite. So there are gyros in there, little small gyros in there that we can point that satellite. And there's the telescope. It's a little tiny 2-inch telescope on the front of it. So it's quite an endeavor, and they do have it up and running. So that's going to kind of be the future for LaserCom is T-Bird. So we do need something on the ground to receive that signal. Right now, we're using a telescope out in California called Mount Palomar, which is actually the Hale telescope, which is a very, very large 200-inch telescope. We're using that to receive it, but we really need to receive it over at the Deep Space Network. So we're going to have to gear up a deep space communications improvement to get LaserCom, which we don't have yet. Now, we're trying to build an operational satellite for laser called Psyche, and that's going to an asteroid. The name of the asteroid is Psyche, and it's going to have a mission like T-Bird mounted on it, and it's going to downlink at Palomar, and that's how we're going to receive the signal from that first operational satellite. But of course, we do need to upgrade the Deep Space Network. And eventually we'll get a module on Artemis, and we'll get this on the moon. And so optical comm will be able to show us, live HD from the moon in real time. And so everybody's pretty excited about that. When, the astronauts were on the moon the last time, we had very, very slow scan video. You probably remember that. It was a 160 line video. And it was, of course, it was black and white. And they did get it up to 320, I believe, by the end, by Apollo 17. So we did have a little bit of improvement, but what we'd like to do is get that up to 1080p or higher, with these laser modules in play. So they are upgrading to a 1 watt pulse laser, and we're looking to get that data link up to well over 200 megabits per second so that we can do HD from the moon. We will outfit one of the 32-meter dishes with a 16-meter optical receiver. That 16-meter, that's a pretty big telescope, but that's a lot bigger than the telescope we're currently using. But that will really give us the gain we need to do these low signal, especially the deep space stuff. So that will happen at the Deep Space Network. We'll outfit one of the big 32-meter dishes, which right now is an RF dish, of course. We'll outfit it with a 16-meter optical receiver. So that'll be, I wish I could do that job. I was a telescope guy. I would love to do that job out in California. Whoever does that is going to make a fortune. 16-meter optical telescope. Wow. So, we're not the only ones doing it. The Japanese have done it. They had a microsat called Socrates, it was. And it was a really small one. They did hit the 10 megabit per second with a 35 milliwatt laser. They didn't use the amplifier. They just used the 35 milliwatt laser. They had just a tiny little 50 millimeter telescope. So that's, basically the size of your camera lens on your 35 millimeter camera. It's a little 50 millimeter lens. But they did something incredibly unique. They did actually get down to what we call quantum limited optical comm. And that means they were able to demonstrate that you could get the data rate high enough that it would only take a single photon to transmit a digital number. So they used a single photon. So that we call that quantum limited space communication. So that's how much data they were able to cram into that signal, that they were getting digital communication using every single photon in the signal, which you've got to be able to do that to use these tiny little 35 milliwatt lasers in orbit. So anyway, that was a real breakthrough that they were able to do that with a single photon. No photon is a 0. A single photon was a 1. So it blows my mind that we're able to do that. It's amazing. Now the Europeans do that too. They've got a system up on their spacecraft. They have a couple of spacecraft that they use for relays. They currently operated at about 1.8 gigabits per second, which is pretty good. And they are continuously using LaserCom and improving their system. But again, it's very low wattage, and it's not anywhere near as reliable as what we eventually will need to do the large wideband missions. So Japan's doing it, Europeans are doing it, we're doing it, we're making progress. So for 2023 and beyond, we've got this migration path. It goes through the space station and Artemis. Hopefully we'll get this set up on the moon, and we will have a breakthrough in the next couple of years. And we can start putting LaserCom on all of our deep space missions. And boy, I'll tell you, I wish we had this on James Webb, because we could get so much more data through the system if we had this available for James Webb. But we will have it available soon for all of our deep space missions.
Please like and subscribe to this channel and press the bell icon to get new video updates.